Welcome back. In this video, we're going to talk about the transformations of functions. The technique of the transformations of functions is a way through which we take functions that we know and we can graphically move them. All of this conversation will be discussed in terms of the graphical representations of our functions, but this can also be done in any kind of context without a graphical representation. Before us right here, I have two of these toolkit functions that we've discussed. I'm showing them here because I'm going to go into more detail and play with them to introduce the idea of transformations of functions. Generally speaking, the technique of the transformations of functions is how to take a base function, one of our toolkit functions, and to change the shape of it by either shifting it vertically, shifting it horizontally, or shrinking it or stretching it. And what we'll be investigating is the effect of multiplying, adding, subtracting different values at different places in our function. This technique has a lot of different applications in advanced mathematics. One of the things is you can take complicated looking functions, rewrite them in a way that you can see them as the transformation of a base function, quickly represent the graph, or other ways that you'll see pretty soon is that you can take something that you say, you know can be modeled by a parabola, but it's not just x squared, but how can you manipulate the x squared graph to fit and model the context you're dealing with? Though this video will just be an introduction to this concept, what we're going to do in this video is take x squared and the square root of x and manipulate these by adding, multiplying different values to different areas of our function. Importantly, this conversation that you'll see is the conversation of when you do something inside of a function and something outside of a function. All right, we're about ready to get started. Before we do this, I just want to look at these two graphs, their tables of values, so we feel comfortable with these, and this will help us in the conversation of transformations. First of all, we have x squared right here. This is upward facing parabola. One important thing to note here is that every x value is squared. When you square then all the negatives and the positives, what you get is this very symmetric shape. In fact, this parabola right here is symmetric about the y-axis, meaning if you took this right here, this shape, and just copied it over, you'd get exactly the same thing. -2 and 2 having the equal outputs helps with that symmetry, or is a requirement of that symmetry. Also here for the square root, I've discussed previously how the square root is really 1/2 of a parabola, just to mention that again. But importantly for this discussion is the fact that we know we cannot take the square root of negative numbers and get a real answer. In other words, those are undefined values. That is the reason this graph isn't represented on the negative part of the x-axis in any way. And then here are just some examples of the values as we plug in x values under the square root. All right, first thing we're going to do is play around with the x squared graph. What I want to do now is I'm going to get rid of my hand-drawn versions here. Let's look at some really nice computer-generated versions and investigate what happens when we add a value to this function inside and outside of the function, and we'll clarify what that means. All right, so as promised, here is a beautiful computer-generated version of x squared. What I want to do now is compare this to the graphs of g of x, which is x squared plus 2, and h of x, which is x plus 2 squared. Importantly to this conversation is that for g of x, we would say we're adding 2 outside of the function. So again, we're basing this on the toolkit function of x squared. We're adding 2 outside of the function. In other words, we could rewrite this statement right here. Given that f of x equals x squared, we could rewrite this as f of x plus 2, where f of x represents the x plus 2. If we wanted to rewrite h of x with this f of x notation, what we would write it as is f of x plus 2. So importantly, for number 1, here we're adding on the outside of the toolkit function. And in this transformation right here, we're adding 2 inside. And again, the function we're talking about is x squared. And we say this is inside because this operation is happening right to the independent variable x before that squaring action happens. But importantly for this conversation, this is a transformation on the inside. Okay, so we have our function f of x equals x squared, our toolkit function. Let's now impose g of x, which is x squared plus 2 onto our graph. And you'll see what it represents is it looks like this parabola has been shifted up. And the question will become is, well, why? Why has it moved in this way? A useful way to analyze these transformations is to look at the table of values. Now, if we look at the table of values here for f of x and g of x, the table of values for f of x is very similar to the one I had represented earlier. But g of x, what is the difference? What's happening between those y values? Or specifically, can you compare the y values for f of x and g of x together? What is their difference? What you'll notice is that the g of x function, all of the y values of the original toolkit function have 2 being added to them. So that's the first really important thing to realize. So what this is, we've added 2 to all the y values. So then to show you what this does to the graph, so if we take away g of x, so we just have f of x equals x squared, but then we take each of those points and we plot them 2 units higher, 2 y value units higher, and then we throw back in g of x, what you'll see is, well, it would make sense that what the g of x function is simply that f of x toolkit function, but all of the y values have been moved up 2 units. So what this represents graphically is the parabola f of x equals x squared has been shifted vertically up 2 units. All right, let's now give the same treatment to h of x. So we have f of x equals x squared. Let's now impose h of x, which is x plus 2 squared. And it might not be exactly what you think. What you might have thought, given what had happened with this first function right here when we added 2 on the outside, maybe you had realized, and this is an important thing actually will be true, is that if you make a transformation inside of a function, it will affect the x values, which is a horizontal change of some sort. In this case, when we do an operation outside of the function, it vertically changes what's going on. And in this case, we might think that if this is an inside transformation affecting the horizontal shifting of this graph, that it would go 2 units on the x-axis, but it actually does the opposite. This went left. It went backwards along the x-axis 2 units. So the question becomes why? Why did this function shift left 2 units and not right 2 units, which you may think would make more sense? The answer is the order of operations, and it's the fact that this addition is happening before the toolkit operation of squaring. But to give you some insight into this might not give you the whole picture, but this is how you could investigate the why behind this right here. And this is the same for all horizontal transformations that we're going to look at. Let's look at x equals -3. So if we plug in x equals -3 into this h of x function, what we get is -3 plus 2 squared. The importance here is we're looking at what is the effect of the addition of 2. For instance, over here, the addition of 2 led directly to adding 2 to all of the y values. But in this case right here, when we add 2 to this x value before we square, we will get -1 squared. So what does that mean? What that means is this addition of 2, the action of adding 2 to the -3, again, we're looking at an x value, what's happening at -3. When we plug that in and add 2 before we square, this function then at x equals -3 is going to act like it did at -1. So whatever the height was at -1 previously, it will now have that same height at -2. That's the reason for that shift to the left. Again, it's the order of operations and the fact that this addition is happening before the squaring. Also, if you look at the table of values for h of x, what you'll notice is that we don't have this addition of 2 like we did between f of x and g of x. Instead, in this case, what you get is, if you can see like where 0 is on f of x and h of x, it's like it's been shifted. The idea is actually it's not the y values that have been shifted, it's the x values because of this action right here. So to sum it up, this is important what this happens. This addition of 2 right here has the effect of subtracting 2 to all the x values And what I mean by that is if you had the original table of values for f of x, but you took those x values and you subtracted 2 from each of them, you would end up with the actual table of values of this shifted h of x function. Importantly, for a graphical representation, what this means is that this was shifted left 2 units. So then to generalize this conversation of shifts, what we get is that we start with our original function, and if we add c to it, what this ends up representing is a shift up of c units. That's exactly the same as this 2 right here. So the shift is shift up c units, whatever you add on there. If we subtract, it's really the same thing, but we're going to shift down. So if we take f of x and we subtract c from it, we're just going to subtract everything from those y values, or subtract c from each of those y values. And what we'll do is we will shift down c units. So then if we took our function and if we add inside of the function, again, the interior, given whatever the function is, again, x squared in this case, we're adding inside that squaring action right there. If we add a value c, then what we actually are going to do is shift left c units. And you may be able to guess, we haven't shown an example here, but if we subtract inside of the function, what we're actually going to do is shift right c units. And again, to state importantly throughout the conversation of transformations, when we do an operation outside of a function, it will have a vertical change, which affects the y values. If we do it inside of a function, that actually is a horizontal shift, which will affect the x values. So in this case right here, I just want to write this for the action of when you actually will apply transformations. If you shift up c units, what you're going to do is you're going to add c to the y values. In this case, if you shift down c units, you're going to subtract c to the y values. In these cases right here, if you add c, which ends up shifting left, what you're actually going to get is you're going to subtract c to the x values. And in this case right here, if we have the subtraction, we're going to have a shift right, which means we're going to add c units to the x values. There's some more important stuff to talk about for transformations, but I want to say is as we go through this, many textbooks have these long lists of the transformations, but these can really be simplified into 2 different ways of thinking about it. First, outside of the function affects the y values. Inside the function affects the x values. The y values get affected how you expect. If you add c, you add c units to the y values. If you subtract c, you subtract c to the y values. The x values will always do the opposite of what you think. In this case, when we add c inside the function, the actual reaction for a table of values or for the points on a graph is to subtract c units from the x. Inside has to do with the x. Now we're subtracting, but it's the opposite for the x's. We're going to add c units to the x. All right, so now what we're going to do is take our friend f of x equals x squared, and we're going to multiply to this function inside and out. And as you may expect, the outside multiplication will be affecting the y values. It's a vertical stretch, we're going to say. And for this, when we multiply inside the function, it's going to affect the horizontal or the x values. We're not going to spend as much time investigating this as we did with the shifts, but you could do a deep thorough investigation in exactly the same way. So what we'll do is look at these individually. So first of all, g of x, which is 2 times x squared. And what you'll see right here is that our parabola has seemingly got skinnier. What's actually happening, and again, if we look at the table of values for f of x and for g of x, you'll notice that all of the y values have been multiplied by 2. This is exactly like what happened with the shifting. If we do something on the outside of the function, it just affects the y values. So importantly right here, what this is, we times 2 to all y values. And what this represents is a vertical stretch by 2. So again, what we say in terms of transformations, what the g of x function is, it's the f of x function, this x squared, but it's been vertically stretched, like it's like a rubber band, and we're pulling it twice as long up. Thus, if we multiply by a value on the outside of our function, we get this vertical stretch. Importantly, if this constant was smaller than 1, it actually would make those y values smaller, and we would call that a shrink. So therefore, if we multiply by a number bigger than 1 on the outside, we call it a stretch. If we multiply on the outside by a number less than 1, we're going to call that a shrink. All right, so now let's look at h of x compared to f of x right here. And you'll notice that h of x looks a lot like g of x. It looks like a skinnier version of this parabola. But what's actually happening here is not a vertical stretch like g of x it was. Instead, as you may guess, it's affecting the x values, and it's a compression. So we're multiplying by 2. We might think if it has a horizontal effect, maybe it's stretching horizontally. But remember, because of the order of operations, and we're doing stuff on the inside, the horizontal transformations are going to be the opposite. When we multiply by 2, we're actually dividing those x values by 2. So if we take each of those x values and move them half the way closer to the y-axis right there, we will end up with the h of x graph. So we can think about this multiplication by 2 having the effect of dividing all the x values by 2, or the same thing, we could say we're multiplying by the reciprocal of 2, we're multiplying by 1/2 to all the x values. This then has the effect of shrinking the graph horizontally by 1/2. So now let's generalize this idea of shrinking and stretching. The easiest, as always, will be what happens vertically right here. So if we multiply by a constant outside of the function that we're looking at, the toolkit, then if c is greater than 1, this is a vertical stretch. By whatever that c value is. Then, if f is less than 1, we're actually going to get a vertical shrink. Because remember, what we're doing is multiplying the y values by this. But if we multiply it by something like 1/3, we wouldn't consider that a stretch because the graph wouldn't vertically get taller, it would get lower. So in this case, if c is between 0 and 1, we call this a vertical shrink by c. And importantly in practice, what this will mean is here we're going to multiply in both these cases by c to the y values. One thing to note real fast is just this little statement I said c is also got to be bigger than 0. That's because we're going to have a separate conversation about what happens with negatives. So in each of these cases, we're only considering c to be a positive constant that we're multiplying or adding for the shifts inside and outside of this function. Let's now move to what happens when we multiply inside. This is always the kind of the weirdest, the most difficult, because these react in the opposite of what we would think. So importantly here, we have this example of this c value right here. What we're going to do is actually multiply all the x values by 1/2. And again, this represents a horizontal shrink. So if c is greater than 1, so in this case, if c is greater than 1, we are going to call this a horizontal shrink. If c is less than 1, it's going to have the opposite effect. So if c is between 0 and 1, this will end up being a horizontal stretch. So just to clarify that, what that means is if I would multiply inside here by something by, let's just say 1/2. This was not a 2, but was a 1/2. In fact, multiplying by 1/2 inside of the function would have the effect of stretching the graph. And the effect will always be the same right here, is that what do we do to apply that transformation? Well, you take the reciprocal of whatever this factor is and you multiply it by the x values. So before I write it, I'll just say this out loud. If we had a multiplying by 2, the effect to our graph, the effect of multiplying by 2 here would be to multiply 1/2 to all our x values. That would give us what that transformation does. If inside the function we were multiplying by 1/2, we would actually multiply our x values by 2. So importantly again, when we multiply by c on the outside of a function, that has the effect of multiplying all of the y values by c, whatever we're multiplying there. The difference in this case is just flipped, is that if we multiply by c on the inside, what we're going to do is actually divide by c, or another way to do it is we're going to multiply by 1 over c to the x values. All right, and I know this is a lot of this. Again, this is just an introduction. You'll see lots of examples of applying transformations. But what I want to do now is move on from x squared and hang out with our friend the square root of x and talk about vertical and horizontal flips. All right, here we have our new friend, the square root of x right here. And again, this has the domain restriction of only positive or non-negative real values, and it only outputs, therefore, positive values. What we're going to do is look at two transformations. So first of all, g of x, which is negative square root of x, and then h of x in this case will be the square root of negative x. And what this is going to do, as I alluded to a second ago, is just discuss the role of negatives. Without further ado, let's look at what g of x then looks like when it's graphed alongside f of x. And what you'll notice, which is kind of fun right here, this now looks like a complete sideways parabola. In fact, what this represents is a vertical flip over the x-axis. The action, which is always important, is we're going to multiply -1 to all the y values. And that results in a vertical flip over the x-axis. And importantly to say is that the square root cannot output negatives, but when the negative's outside here, knowing this will output a 0 or positive, when you throw a negative on the outside, then you'll know that all the outputs for this function, g of x, will all be negatives. Now, what happens when we throw the negative on the inside? Let's now look at h of x, and maybe that's what you'd expect. Or maybe if you've been following along, maybe thinking, well, I'm guessing it's going to do something really trippy and weird. Actually, this is the nicest of the inside transformations, the horizontal transformations. In this case right here, if we have a negative inside the function, what happens is we actually are going to multiply by -1 to all of the x values. And what that ends up representing is a horizontal flip about the y-axis. And importantly, again, to generalize, when you look at a textbook, they often have these huge tables of these transformations, but it really comes down to this. If you interact with the outside of a function, so outside of the square root, outside of the squaring, you will affect vertically what's happening to the graph. Adding or subtracting is all about shifting. Multiplying or dividing is all about vertically stretching or shrinking. And when you act on the inside of the function, you're going to have a horizontal transformation, shifting or stretching or compressing. And with all of the inner transformations, it does the opposite of what you'd think. If you're adding, you're actually going to affect the x values by subtracting. If you're subtracting, they're adding. If you're multiplying by a value, you're going to end up dividing or multiplying by the reciprocal.